All right, welcome back, Algebra 2. Like I say that every time. I say welcome back, but I don't get to see you. It's kind of sad. All right, so we finished up our Unit 14 on all of the sequences and series with a test last week, kind of a take-home test that you should have hopefully finished at the latest by the end of the day today, and upload that to OneNote. I'll get those graded as you guys turn them in. Give me a little bit of time and we'll get those in. Hopefully those will help your grades a little bit because they're a bigger grade and it was a use your notes test, right? All right, so our next unit, we're going to kind of cut these last two units really short and just do some basics in each of them. So our first one normally leads into probability and how to find probabilities of events. But before we can talk about probability, we're going to talk about counting the number of possibilities of events happening. So a lot of times, for this first example that's on here, we want to know how many different outcomes there are in a situation. Because if I know the number of outcomes, then eventually I can find the probability of that outcome happening, right? Think about like, what's the probability of me winning the lottery? Well, I have to know how many different ways there are to win the lottery if I want to know my probability of it. Okay, so that's where we start. So a lot of times you can, where we first learn about finding the number of possibilities by making a tree diagram. So let's say you want to make a sandwich for lunch. You go into your kitchen, you have white bread and wheat bread, you have Swiss cheese and cheddar cheese, you have ham, turkey, or tuna to put on your sandwich. Now, obviously, you could combine a bunch of these, but if I just wanted to use one from each of those categories, I can figure out how many sandwiches. So in my first choice here, I can pick my bread, right? So do I want white bread or wheat bread? And then based on what choice there, I'm going to choose my cheese. So from white bread, I can pick Swiss or I can pick cheddar. Or from wheat bread, I can pick Swiss or cheddar. And then once I make that choice, then I've got 3 more choices from each of those, right? So I kind of make this little tree diagram. And then if I count all my outcomes over here to see how many total sandwiches, there's 12 of them, right? So that's one way. Now, if I get into more possibilities than just bread, cheese, and meat, like what if we think about mayonnaise or mustard, lettuce, tomato, or pickle, toast your sandwich or not toast your sandwich, this tree gets really big and nobody wants to draw all of that out. So we are instead going to use what we call the fundamental counting principle, which basically just says that if you can do something a certain number of ways, and then you can do something else a certain number of ways, and so on, you just multiply the number of ways you can do each event, and that gives you the total outcome. So for our tree diagram we just did, we had 2 types of bread, and then we had 2 types of cheese, and then we had 3 types of meat. So if I multiply 2 times 3, I get 12 different sandwiches. Okay, so that's our fundamental counting principle to figure out how many different ways you can do something. First way we look at it. All right, so let's try a few examples with this. This is one of my favorites because whenever we talk about multiple choice questions and you guys talk about like, oh, I just pick C every time if I don't know or whatever. There are a lot of different ways to answer a multiple choice test. Okay, so it has 8 questions, right? And then there are 4 possible choices for each question. Okay, so a lot of time on these, I like to kind of make myself little blanks for my possibilities. So I'm going to make 8 questions. So question 1, question 2, question 3, 4, 5, 6, 7, 8, right? There are 8 different questions on that test. And then each question has 4 possible choices. So A, B, C, D. So this first question has 4 choices. Next question, 4 choices, and so on, right? Every question on that test has 4 different choices. So then I would just multiply all of those, right? Because think about like the first question, I'd have 4 choices. So like A, B, C, D. And then from that A, I'd have 4 more choices for my second question. And it'd make this huge branch of a tree, right? So that's kind of how you're thinking of it. And then that's basically 4 to the 8th power. And if we plug that into our handy dandy calculator, we get 65,536. So there are 65,536 ways that I could give answers to that test, right? 65,536 different ways to give your answers on that test. That's a lot, right? That's why we say don't guess. All right, next one. Same kind of idea. This time we're going to talk about police using photographs of various facial features to help witnesses identify suspects. One of these identification kits comes with 195 different hairlines, 99 eyes and eyebrows, 89 noses, 105 mouths, and 74 chins and cheeks. The developer of this kit claims that it can produce billions of different faces. So we want to find out, is this correct? So basically, we want to find out how many different faces can this produce. Well, to make a face, I'm going to use one from each of these categories, right? So basically, those are all my different options. So I have 195 different hairlines times 99 eyes times 89 noses times 105 mouths times 74 chins and cheeks, right? We're going to get a pretty big number there when we put this in our calculator. So if I type it in here, 195 times 99 times 89 times 105 times 74. Ooh, that gives me a number in scientific notation on my calculator. So I tried not to make them too big on homework and such, but just a heads up, if you do get a big number in your calculator, sometimes it will automatically show it in scientific notation. Let's see. Okay, so that would be 1, 3, 3, 4, 9, 9, 8, 6, 6, 5, 0. That is a big number, right? So if I put in my commas here, well, are they correct that it can produce billions of faces? Well, that's my hundreds, thousands, millions, and billions. So I get a number of about 13 billion here. So yes, this is correct because we get at least 13 billion faces, right? Okay, so the next part of this says a witness can clearly remember the hairline and the eyes and eyebrows of a suspect. So if she can pick those, we don't have to include that in our choices. So I'm not going to worry about hairlines. I'm not going to worry about eyes and eyebrows, which means we just have to do noses times mouths times chins and cheeks. And then if we do that in our calculator, we get 691,530 different faces. Far fewer, right? So if you know a few pieces of that, then you've got less faces to choose from. Okay. There's another really popular one that we see a lot, and that's about license plates, right? So if you look at a standard Indiana license plate, there's usually 3 letters followed by 3 digits. Oh, I wrote that backwards, didn't I? These should actually be switched so we can think about the right way. So it's 3 digits followed by 3 letters. That's what our license plate looks like over here, right? Number, 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 letter, letter, letter. All right, we want to know how many different license plates are possible if the digits and the letters can be repeated. Okay, so I've got 6 places for numbers or letters on my license plate. So I'm going to make 6 blanks. 3, 4, 5, 6, right? The first spot, if I do it right here, this first spot should be a digit, right? So if you think of a digit, it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's 10 different possibilities for that, right? Because I could have 0. Don't forget about 0. That makes it 10 numbers there. Okay, so then we're going to say that they can be repeated, right? So then for my next one, it's another digit. I still have 10 choices because I can use any number. And then for my third digit, again, it would be 10 choices. All right, then I'm going to do my letters. So how many letters are in the alphabet? There are 26. And then I could pick another letter and another letter, right? So I've got 10 choices for digits, 26 choices for letters, and I can repeat them. So I've got that same number of choices every time. So then if I remember we're going to multiply all of these numbers, right? So 26 to the third power times 10 to the third power would give us 175,760,000. Put in our commas there. There are 17,576,000 different license plates that can be made using that method, right? If we're allowed to repeat letters and digits. Okay, so the next part, we will do the same thing. How many different license plates are possible if we cannot repeat those numbers? right? Okay, so now I have my same 6 spaces, but this time I can't repeat. So for my first digit here, I've got 10 possible digits, right? 0 through 9. But then when I go to pick my next number on my license plate, it can't be the same as that number. It has to be different, right? So if that has to be a different number, then now I only have 9 choices because I've already used whatever number that first one was, right? So then my next number has to be different again from the first 2 numbers I've already used. So now I only have 8 choices. So remember when you put these numbers here, these are not the actual numbers on the license plate. These are the number of choices of numbers that you have, right? So for my first number, I have 10. My second number, I only have 9 choices because I've already used one. And then my third number, I have 8 choices because I've already used 2 of the numbers. Same thing with the letters. For my first letter, I'm going to have 26 choices, but then I've already used a letter. So my next letter, I have 25 choices. And then my last letter, I would have 24 choices. And then we're going to multiply all of those numbers. It's 26. And we get 1, 1, 2, 3, 2, 0, 0, 0. So that is a slightly smaller number because now I'm taking out all of those license plates that had repeated numbers or letters, right? So you would expect that number to be a little bit smaller. Okay, so that's an important distinction when you're doing these counting principles is pay attention to whether things can be repeated or if they can't be repeated. That makes a big difference. Okay, next. So what we've kind of been doing, or we've been talking about the basic counting principle. Now there are a couple specific types of counting that we're going to do. One's called permutations, the other's called combinations, and we'll get there. Okay, so an ordering of n objects is a permutation of the objects. 2 important words there. Ordering is a permutation, right? So permutation is always when order matters. That is something you will hear me say a lot in the next couple days as we talk about that. So permutation, order matters. It means when I decide how many possibilities there are, the order of each possibility means it's different from the other one, okay? So for instance, if I want to find the number of permutations of the 4 letters P, Q, R, and S, basically what I'm asking you to do is how many different ways can you order those 4 letters, right? Now I could start this by just writing out all of these different orders and counting them up. So like I could do P, Q, R, S. That's one way to order the 4 letters. I could do P, R, Q, S, right? I could do, let's see, actually, yeah, P, Q, S, R, right? We could do P, R, S, Q. And I can keep going with all of these. I could also do, let's see, P, S, R, Q, and P, S, Q, R, right? So right there, I've got 1, 2, 3, 4, 5, 6 total different possibilities. So that's one way to think about this is how many different ways can you order it? Now, then I would have to do like where Q is first, and then when R is first, and then when S is first, right? But every way I change those letters around, it is a new permutation of those letters. We could also think of this like we just did in the other problems. So basically, I'm doing this, right? And looking at how many options I have. I have 4 letters, so 1, 2, 3, 4 blanks. When I go to pick my first letter, I have 4 choices. I can pick P, Q, R, or S. So I have 4 choices, right? Now I'm doing orders, so I don't want to repeat them. So I'm going to have to pick a different letter for my second choice. But I've already used one of the letters, so I have 3 choices. And then I would have 2 choices, and then I'd have 1 letter left to go there, right? So then 4, 3, 2, 1, if I multiply those, that would give me 24 different arrangements of those letters. And I promise if you sit and write them all out, it works, right? And you can kind of think of it this way. There's 1, 2, 3, 4, 5, 6 starting with P. So there's going to be 6 that start with Q, 6 that start with R, and 6 that start with S. Or the kind of quicker way to do it is to think through those possibilities. There's one other much quicker way to do this, and that is by thinking of this as what it is, a permutation. So a permutation for any positive integer n, that product n times n minus 1 times n minus 2 until you get to 3, 2, 1 can be written as an n with an exclamation point, and that is read as n factorial. And that's a new word that we'll use. But anytime you hear somebody say you need to calculate a number with an exclamation or a number factorial, that means to do what we did here, right? 4 times 3 times 2 times 1. This is the same as 4 factorial. That's what that means, right? 4 factorial means 4 times 3 times 2 times 1. Okay, so there's another way to think of it. The other nice thing is there is a button for factorial on your calculator. A lot of you will probably see it as a second function button somewhere on your calculator, but you'll just see an exclamation point, or it might be an X with an exclamation point next to it. There will be a couple of you where you have to actually kind of go find this in your calculator. Sometimes it's under the math menu, and then you might have to look for like probability or something like that to find it there. Let me know if you can't find it, but there is a button somewhere on your calculator if you have a scientific calculator that has that exclamation point, so you can do that there. Okay, so let's kind of use that to do a few other examples here. So we've got 12 skiers competing in the final round of the Olympic freestyle skiing aerial competition. We want to know how many different ways can the skiers finish the competition, assuming that there's no ties, right? So everybody has to come in a different place. Well, we've got 12 skiers, right? Okay, so basically that means that if I've got 12 spaces for them to finish, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Well, then for the, let's say, first place finishers, there's 12 options. The second place, there'd be 11 options, and so on and so forth, right? Now, I don't need to write out all of those numbers because I know it has to go all the way. So I know that if I want 12 skiers and I want to know how many different orders can they finish in, right? So we know that this is a permutation because we know that order matters. Order matters because we're looking at the place that everybody finishes in, right? So if Joe finishes first and Bob finishes second, that's different than Bob finishing first and Joe finishing second, right? So places mean permutations. So if I want the number of permutations, then I can just do 12 skiers and I can do 12 factorial. And you can either do 12 times 11 times 10 and type all those into your calculator. It takes a minute. Or if you found that lovely factorial button, you can hit that. And we get 4, 7, 9, 0, 0, 1, 6, 0, 0. So there are 479,001,600 possible ways for those 12 skiers to finish that race, okay, in all different places. Okay, next is how many different ways can the skiers finish first, second, and third to win the gold, silver, and bronze medals? Well, in this case, we're not looking at all 12 skiers, right? So really, we just need the first place, the second place, and the third place, right? So this is first, second, and third place winners. But we still have 12 skiers, right? But we're only going to look at the first 3 places. So then all we have to think about is, okay, well, there would be 12 possibilities for the first place skier. There's 11 possibilities for the second place because we've already picked the first place. And then there'd be 10 possibilities for that. So in this case, we don't need the whole 12 factorial. We only need part of it. So 12 times 11 times 10 would be 1,320 possible ways to pick the first, second, or for the first, second, and third place finishers to win, right? Much fewer ways because we're only looking at the first 3 places, okay? Okay, but both of those are permutations because order matters, right? Again, the first, second, third place would be different if I changed the people around, okay? All right, that second example, example 5B, is an example of where we're doing permutations of so many objects or so many things taken from a bigger group of things. So a lot of times you'll see this written in math language like this here, And what this means, the P here stands for permutation, right? That means our order matters. The N are your total objects or things or people or whatever they are. And then the R is the number of objects chosen, or how many you're picking from the total, okay? So we can do that with a formula. So if you want to think about that up here with this formula, so up here I had 12 skiers, right? So I'm going to do a permutation of 12 total skiers, but I'm only going to pick 3 of them because I just need the first, second, and third place. So you can use this formula here to figure it out. Now, I don't care which way you do the problem. If you do it this way, like I did, where I just thought of 12 possibilities, 11 and then 10, you can multiply and get your answer that way. Or if you want to always use the formula, you can do it this way. So I'm going to do the total number of things, which would be 12 total skiers, so 12 factorial. And then on the bottom, I'm going to do the total minus how many I'm picking. So 12 minus 3 would be 9 factorial. And then I'll kind of go through how to do the math on the next problem like this, but if you do that math, you'll still get 1,320. Okay? Okay, so let's try a few using that formula here, or try one. You are considering 10 different colleges to go to. Before you decide to apply, you want to visit some or all of them. So in how many different orders can you visit 6 of the college? Now again, here's your key word, right? We want to know how many different orders you can visit the 6 colleges. That word order means permutations, right? Okay, so I want to visit 6 of the 10 colleges, right? So we just said we know it's a permutation because the order matters. We have 10 total colleges, and we're going to choose 6 of them to visit. Okay, so using that formula, I do my total number on top, so 10 factorial, and then on the bottom, I'm going to do my total minus how many I'm choosing, that number factorial. So that would be 10 factorial divided by 4 factorial. Okay, now if you want to think of this way, now you can do find the top number, find the bottom number, and divide them in your calculator, that's fine. Or you can also think of it as that 10 factorial, that's 10, 9, times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1, over 4 factorial is 4 times 3 times 2 times 1. And then I could cross out the 4s, the 3s, the 2s, and the 1s, and I just have this piece left, right? And think about it, if you're choosing the 6 colleges, you'd have 10 choices, 9 choices, 8, 7, 6, 5 choices in each thing. So that's one way to do the math there. You can use your calculator to do the math. Whatever way you decide is easiest for you, that's fine with me. And that would give us a total of 30,240 different ways or different orders that you could visit those colleges. Okay. Okay, and then the next one, how many different orders could you visit all 10 of the colleges, right? So you can do this either way. Again, if you want to use that same formula, that's a permutation of 10 things and I'm choosing all 10 of them. So if I plug that in, I get 10 factorial. And on the bottom, I get 10 minus 10 factorial, right? Now here's something that's a little bit tricky. That's 10 factorial over 0 factorial. If you put 0 factorial in your calculator, it will show you, but 0 factorial, 0 factorial is actually just 1. So we end up with 10 factorial over 1. Okay, so basically the answer here is just 10 factorial. And you can think about that because you're not really doing 10 and then choosing a certain part of them. You're choosing all of them. So if I want to visit all 10, and I just want to know the number of orders, then my answer is just 10 factorial. And we can do that in our calculator. We get 362,880. So there's how many different orders we could visit all 10 of the colleges. Okay. All right. Next up, permutations with repetition. Okay, so sometimes we're doing permutations, but things repeat. And if there's repeats, then that doesn't make a new order of the objects. I'll kind of show you how this works. One way to see these easily is with words and rearranging the letters in the words. So let's say I have the word Ohio, and I want to come up with how many different ways can I reorder those letters to make different arrangements, right? So that's where you'll see this distinguishable permutations. So permutations tells us we know order matters, right? But distinguishable. So for instance, like if I call this O01 and this O02, if I change it and make it O2 HI and O1, it's still, even though I switched the O's, those still look the same. So those are not distinguishable, right? So this is where distinguishable, that's one word. This is where I have to divide out the repeats to find out how many total permutations there are, because I don't want to count the ones like this, where the O's are still technically the same, even though they're different O's. Okay, so if you have repeats of items, we're going to divide out the repeats. Okay, so using the formula that's up here, right, I want to take the n factorial. That's my total number of objects. So there are 4 letters. Oops. 4 letters in the word, come on, 4 letters in the word Ohio, right? So that means I have 4 total objects that I'm finding the orders of, right? 4 factorial would be the number of ways I could order 4 things. But I'm going to divide by anything that repeats. So there are 2 O's, right? That is my repeat. So I'm going to divide by 2 factorial. Okay, and again, you can put that in your calculator. If I think of 4, 3, 2, 1 over 2 times 1, the 2's and the 1's cancel, and we end up with 12 different ways that we can reorder that word to be distinguishable different words. Not really words, but rearrangements of the letters. Okay, arrangements, by the way, is another way you'll see orders or permutations. It's another good word. Think of how you're arranging the letters. Okay, let's do another one. Mississippi, same thing, right? So I've got some repeats of my letters here. Total letters, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total letters, right? We've got 11 total letters, and I like to kind of write these out so I don't forget what I'm doing. There's only one M, so that's good. There are 1, 2, 3, 4 I's, and then 1, 2, 3, 4 S's, and I've got 2 P's, right? So this time more than one thing repeats. So we have to think about all of those repeats, right? Okay, so 11 total letters, so that's 11 factorial on top, and then we're going to divide by all of the repeats. So the 4 factorial, that divides out our I repeats. Another 4 factorial divides out our S repeats, and a 2 factorial will divide out the P repeats. Okay, now again, you can type that in your calculator. Use your parentheses wisely if you're going to type it all in at the same time. Or you can write it out if you want to. So 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1, right? And then the bottom, though, we've got 4, 3, 2, 1, and then another 4, 3, 2, 1, and then a 2 and a 1, right? So you can start crossing stuff out. All the 1s really don't matter. So don't care about those. I can cross out this 2 and that 2, and then a 3 and a 4, and a 3 and a 4. And you can simplify these as well. So like this 2 and this 6, I could make that a 1 and a 3. This 2 and this 8, I can make that a 1 and a 4. Then I can cross out the 4 and the 4. And then the 3 and the 9, I can make that a 1 and a 3, right? So then across the top, I'm just going to do 11 times 10 times 3 times 7 times 3 times 5. And we get 34,650. There are 34,650 distinguishable ways we can rearrange or reorder the letters in Mississippi. Okay, So when there's repeats, we have to divide those out. Okay, another good thing to think of there. Also, to kind of notice that like we talked about repeats here, like when, where did we do the repeats? Oh, here we talked about, when things can repeat and when things can't. That was on our counting problems. It's a little bit different than like dividing out the repeats. There's kind of different ways to think about those. Okay, next up, combinations instead of permutations. So combinations are very similar. The big key difference, order does not matter with combinations, right? So we talked about like people finishing a race, right? They finish in certain places. So first place, second place, third place, that's when order matters. Another good order matter situation, a telephone number, right? If I dial 911, that's not the same as dialing 191. Those are two totally different telephone numbers. So things where order doesn't matter. One big example that people use is cards being dealt, right? If you go to play poker, playing poker with a 5-card hand, if I deal you 5 cards, it doesn't matter what order I deal those cards in. So order doesn't matter here. So in this case, we don't want to count every single possibility. We only want to count possibilities that are different even if we change the order. So I could say like A, B, C and CBA, these are the same, right? If those things are the same, then order doesn't matter. And we'll kind of see some examples of that, right? So I talked about, the cards is a big thing, right? If you get a hand of cards, and let's say you got like a 1, a 3, not a 1, there's no 1 in cards. Let's call it an ace, a 3, a 5, and a 6, right? That's the same as having 6, 3, 5, and ace. I can change the order around, right? These are the same hand of cards. They're just in a different order. So when we talk about combinations, now here we've got a C for combination. And notice you've still got N is your total number of objects, and R is the number of objects you're picking, right? The only difference is this little guy right there. So with combinations, that dividing by R factorial, that divides out all these ones where the same objects are there, so the order doesn't matter, okay? Okay, so to find combinations using our formula here, say we've got a standard deck of cards, it's got 52 cards. There are 4 suits, spades, clubs, hearts, and diamonds, right? So 52 divided by 4, that means there's 13 cards in each suit. Okay, so we want to know how many different 5-card hands are possible, right? So 52 cards, how many different hands can I have that have 5 cards, right? Because like I said up here, like ace 3 5 6 is the same as 6 3 5 8 or 6 3 5 ace. This means order doesn't matter. Doesn't matter what order the cards are in my hand. I would still have the same hand. So this is our combination, right? Now there are 52 total cards, and I want to know how many different ways can I pick 5 of those cards, right? Okay, so then if we use our formula, we would do 52 factorial over, I'm going to do 52 minus 5, and then another times 5 factorial. Okay, so now if I do that subtraction, we get 52 factorial. Subtract 5 would make 47 factorial, and then 5 factorial. Okay, now here again is where you can think like that 47, if I wrote out all of these numbers, which I don't want to do, 47 and down is going to cancel out, right? So this 47 and all of the 47 part up here is all going to be gone. So I would just have left 52, 51, 50, 49, and 48. 47 and on is all going to cancel out with what was on the bottom, right? So then on the bottom, actually, if you want to see it cancel out, we'll do it this way. So then 47 factorial. On the bottom, we got our 47 factorial, and then the 5 factorial is 5, 4, 3, 2, and 1. So that's where those 47s cancel out and they go away, right? Okay, so then you can do a little more canceling here again. The 2 and the 48, I can make 1 and 24. The 3 would go into 51. That makes 1 and 17. My 4 goes into 52, and that makes 13. And my 5 goes into the 50, that makes a 10. Right? So if you want to do all the canceling, you can. If you want to just type it into your calculator, you can do it that way. So then if I multiply 13 times 17 times 10 times 49 times 24, I get 2598960. So 2,598,960 different 5-card hands you can deal from a standard deck of cards, right? This is the beginning of learning how to count cards, right, guys? Good luck. It's a hard thing to do, but that's how many different cards you could get. Okay, so in how many of these hands are all 5 cards the same suit? Okay, so to make these choices, it's a little bit different. We're not going to go from all 52 cards, but we do have to do 2 different things, right? So if I want all 5 cards to be the same suit, well, first I have to pick one of the 4 suits, because I could have all 5 spades, all 5 clubs, all 5 hearts, or all 5 diamonds, right? So first we've got to do a combination where I've got 4 suits, and then I have to pick one of those, right? And then from those 4 suits, I'm going to have to do another combination, because within that suit of spades, right? Let's say it's spades, then I've got 13 cards in that one suit, right? There are 13 cards in each suit, but I only need 5 of them. So we've got 2 things. And this is where I need to do both of these things, right? I'm going to choose a suit. I'm going to choose the suit. And I'm going to choose 5 cards, right? If there's an and in between when you have to do more than one combination, then this is going to be a multiplication, because you have to do the first thing and you have to do the second thing. I've got to choose a suit and I have to choose 5 cards, right? Okay, so this first one, I'm going to do a combination of 4 and then choose one of those things. That'd be 4 factorial over 4 minus 1 is 3 factorial, and then 1 factorial. And then the 13 choose 5 would be 13 factorial. 13 minus 5 is 8 factorial, and then 5 factorial. Okay, and we're going to multiply those 2 numbers. Now, 4 choose 1, you'll kind of get used to this. Notice that the 3, 2, 1 is going to cancel out on both of those. So anytime you have a number choose 1, it's always just going to be that number 4, right? If I've got 4 things, how many ways are there to choose just one of them? There's 4 ways, okay? And then the other one, the 13 factorial divided by, this one I'm just going to use my calculator. 13 factorial, I'm going to divide by 8 factorial. And then I'm going to divide by 5 factorial. I get 1,287. So then if I multiply those 2 numbers, I get 5,148. So there are 5,148 different hands you could get where all of the card or all 5 cards are the same suit. Okay, so sometimes you'll have to do a problem where there's more than one. We won't do a lot of those, so we'll try a couple. Okay, next one, restaurant serves omelets that can be ordered with any of the ingredients shown. We want exactly 2 vegetarian and 1 meat. How many different omelets could you order? Okay, so notice that word and, right? That's going to be important for us. So I want to start with 2 vegetarian. Well, there's 1, 2, 3, 4, 5, 6 total vegetarian things, and there are 4 meats, right? So I'm doing 2 different things. I'm going to need 2 combinations. So my first one, got a combination where I have 6 vegetarian ingredients, and I want to pick 2 of those. And so I'm going to multiply. I've got 4 meat ingredients, and I'm going to choose 1 of those. Okay, now again, we just talked about if you ever get something choose 1, that's just that number. 4 choose 1 is 4. And then 6 choose 2, that's going to be 6 factorial, divided by 6 minus 2 is 4 factorial, and then 2 factorial. Okay, so then if we do that one, let's see, the 4, 3, 2, 1 would be gone. So we're going to get 15 times 4, which will give us 60 total ways, or 60 different omelets. I can spell omelet that you can order. Okay, picking only 2 vegetarian ingredients and 1 meat, you could make 60 different omelets. That's still a lot, right? Okay. The next part, now I'm going to say that I can afford at most 3 ingredients in my omelet, right? So the most I can get is 3 different ingredients. Okay, so now I want to know, how many different ways can I do that? Well, this one gets a little bit more complicated. Do I need to say vegetarian on that one? I guess we can do both. Okay, so here we've got to think of different possibilities, right? Because it could be that I decide to pick 0 ingredients in my omelet. I could put 1 ingredient in my omelet. I could pick 2, or I could pick 3, but I'm going to stop there. I'm not going to pick any more than 3 ingredients, right? So I've got different options here. I can pick 0 ingredients, and I guess that's just eggs, right? I could have 1 ingredient. I could have 2 ingredients, or I could pick 3 ingredients, right? We want to look at all of these possibilities. Now notice that as I said 0 or 1 or 2 or 3, right? These are or options. So if we're doing or, we're going to add the possibilities, right? Okay, so if I'm going to pick 0 ingredients, now here's the other problem here is we've got vegetarian and we have meat, but we don't really care which is which. So I'm just going to put them all together. We have 10 total ingredients, right? It doesn't say they have to be one or the other, so I'm just going to go with the 10 total. Okay, so if I pick 0, that would be a combination, because it doesn't matter what order I pick my ingredients in, they're all going the same place. I have 10 options and I'm going to pick 0 of them. That's one possibility. Or I could have 10 options and pick 1 of them. I could have 10 options and pick 2 of them. Or I could have 10 options and pick 3. And again, because it's or, now I'm going to add my options, right? Up on top, I wanted 2 ingredients and 1 meat ingredient. I knew exactly what I wanted, so I did a multiply. Here, I've got different possibilities, so I'm going to add them. Okay, so 10 choose 0. This is another common thing. Anything choose 0. If you think about that one, if I have 10 things and I'm not going to pick any of them, how many different ways are there to pick none of them? There's only one way, right? I'm not going to pick anything. So anything choose 0 is just 1. Okay, 10 choose 1. Anytime we have 10 and we're just picking 1, that's always going to be just 10. 10 choose 2. This one we can write out. So 10 factorial. That would be 10 minus 2 is 8, and then 2. And our last one is 10 choose 3. So 10 factorial. 10 minus 3 is 7, and then 3. Okay, so that would give us 1 plus 10. That one's going to be 45 if I put that in there. And my last one will give us 120. Again, I'm just using my calculator with the factorial there to figure those out. So then if we add those all up, we get, do my calculator just to make sure I do it right here. We get 176, right? There are 176 different omelets we could make if we wanted to pick at the most 3 ingredients. So that means I could pick 3 or 2 or 1 or 0. All our different options, okay? Those are a little bit more complicated. You just got to think about them, okay? All right, so combinations, permutations, thinking about repeats sometimes, and counting principle. There's a lot to these, and every problem is very different. So like I said, we're going to kind of do the basics here. I just wanted you guys to watch today. You now have a 3 problem homework. It is very simple. I just want to see that you got something out of watching this video. So that'll be on a Google form. Go fill that out for me. Get it done. Do it now. It should only take you like 5 or 10 minutes. It will not take you very long. So go get that done now that you've watched the video. And then in our next class, you'll get a full homework with some examples from me to kind of help guide you through all of the homework problems. And then we'll do an assessment over this stuff probably at the end of next week. Okay. All right, guys, have a good one.